Okay, let's look at an example now. Here's our figure that we're dealing with, so we know that these two angles are equivalent by the way we drew just one angle bar here. And these two angles that with the double bars, those two are also equivalent. And then we've got this one side labeled length 5. We need to prove from that figure that the line segment AD, this is the point A right here, AD is also equal to 5. So notice that this line segment breaks us up into two triangles. Let's see if we can prove those two triangles are congruent. Well, for starters, the side AC, that side right there, is congruent to itself, the reflexive law for congruence. And that side is a side of two distinct triangles, this one and this one. So triangle ABC from here to here to here is congruent to triangle ADC from here to here to here. Why would that be? Well, notice that we have angle, common angle, side, and another common angle. What I mean by that is these two angles are congruent. So if we go angle, side, angle, or from this triangle, angle, side, angle, we have that these two triangles are congruent. Okay, because of that, because they are congruent, I know that AD, that side, has the same length as AB because they are corresponding parts of congruent triangles. So therefore, I'm going to say CPCFC. We can write this a lot. Corresponding parts of congruent figures are congruent. Well, that gives it away. This side has to be length 5. If these two are congruent and this one is length 5, that gives us that AD is also 5. That's basically the definition of congruence. Two congruent line segments have the same length. Next, let's look at the definition of an isosceles triangle. You probably already know this. An isosceles triangle is a triangle with two congruent sides. And here are some terms we need to know about isosceles triangles. Let's label all of these. Let's label the vertex. Well, the vertex, frequently the corner points are called vertices. But the vertex is the one up here, the one that is attached to the two sides that are equal length. Let's go ahead and do that. Those two sides are congruent. All right, the vertex angle, that'd be this angle right here. So vertex angle is this one right here. The legs I've already labeled as being equal length sides. The two legs that have the same length, they're the legs. The two sides that have the same length. The base is the other side. The base is that side. And then the base angles, they're already drawn in like this. I made it look like they're the same angles, which they are in an isosceles triangle. And that's actually what the next theorem says. A triangle is isosceles if and only if, that double arrow means if and only if, like I abbreviate it with IFF. A triangle is isosceles if and only if two of its angles are congruent. Okay, let's finish up this video with a lemma. In a triangle ABC, if these two sides are equivalent, then angles A and angle B are also equivalent. Let's draw the picture. Okay, I need two congruent sides. I'll make it this one and this one. So let's label this as, if it's AC and BC, that's got to be C right there. AC and BC are congruent. We're going to prove that these two base angles are congruent. I won't draw it there just yet, but we're going to prove angle A and angle B are congruent to each other. All right, so by the SAS postulate, believe it or not, we have two congruent triangles right here. The first one is triangle ACB. ACB. Okay, what is that congruent to? Well, it's congruent to BCA triangle. BCA. How do we know that? Well, they have the common angle C, which I'll put 2 bars there. So we have side, angle, side. Side, angle, side. So we could say by SAS that these two triangles are equivalent. Well, what does that mean? Corresponding parts of corresponding figures are congruent. Angle A and angle B, notice in the order here, angle A is congruent to angle B. Angle C is congruent to angle C. Angle B is congruent to angle A. So that completes the proof.